just 1 minute left. We can start if you like, so we can save time. Yeah, so today we will study experimentally how to get the ratio E over M. And this is very nice. And let's show you that before we start. So I'm happy that we have like 2 sets here. So you can see this very nice light that you can see right here. Actually, this light created by the de-excited electrons. Actually, the electrons that are moving doesn't create any light. But this was created by de-excited electrons. So this is very nice. We can see that this something tells us that there are some electrons moving. If I do something like this, you can see what will happen to that trajectory. So it has smaller radius and larger radius. But what's the reason for that? So why do we have this kind of phenomenon? Let's try to come to the whiteboard and try to explain why do we have this kind of phenomenon here. I will start with just what I explained to you today. We'll just make sure that the camera is working so we don't lose anything. So let's start with this idea. We mentioned, guys, that the electrons can be affected with the magnetic field or by the magnetic field. So if we have a magnetic field and we have an electron moving with initial velocity, so that electron will start to circle, will start to zip around the center of circular path, as you can see. What's the reason for that? The reason for that, guys, we have 2 forces, and those 2 forces are balanced. So we have centripetal force and we have magnetic force. And those 2 forces act on this electron and keep the electron moving and keep this tangential velocity constant and never change. So just the direction of this velocity is changing. However, the magnitude never changes. Changing the direction of this tangential velocity can create something called centripetal acceleration and also centripetal force. That's very nice. So the magnetic field that you can see right here actually is toward the whiteboard. So if we use the left hand again, so what we can have magnetic field, velocity, see that again. So magnetic field, velocity. Let's do this again. So we have magnetic field and velocity. So V cross B, so that gives me F. Yeah. I think we have another problem here. So, since the magnetic field is in the board and the velocity is down, so what does that mean? That means the magnetic force should be in that direction.
Except for the electron, so it's a holo.
Yeah, but even with that, so
like
if we have
you
negative
use the
sign,
right
that
hand.
means the velocity can reverse its direction if we have negative sign. So let me correct that for you guys. So we will just do that. So the velocity should be in this direction instead of being down. Yeah. So now it should be, we should be okay. So we have magnetic field, we have velocity, so the magnetic force now toward the center of the circular path. Okay, so try that again. So we have magnetic field in the board, the velocity up, and the magnetic force toward the center. How we know that that I have velocity here, a magnetic field here, and magnetic force here. So how do we know that? We can use the right hand. So we have V cross B. So V cross B, that gives me F. If we have B cross V, so that will give me F down in the opposite direction. So if we do that, I will try to do that, yeah. So V cross B, so V is going on the whiteboard. So you have V cross B, that will give me FB in this direction. Is that good? This is how can you use the left hand to figure out the direction of the magnetic force. So why do we need to use the right hand? The right hand, guys, can give you this rule. So we always need to multiply V by B. So we need to have V cross B. If we have B cross B, so that means we will have negative sign. So that's why V, B, so B cross B, that will give me F. Okay, that's very nice. Now, if everything is balanced, what does that mean? That means the magnetic force is equal to the centripetal force. So we'll have this very nice equation that we had today. And we will have the electron charge, the tangential velocity of the electron, and I think I need to use here a small letter, which is E, just to indicate that we have the velocity, the tangential velocity of the electron. Times magnetic field, and that will give me the mass of the electron, the tangential velocity of the electron squared divided by r. What is r? R is the radius of this circular path. Now, I explained all of that here for you guys. Now, let's see this equation. This equation can give me the ratio E over m, the charge of the electron over the mass of the electron. But there is just one problem here. We don't know this tangential velocity. So how can we figure out this tangential velocity? To do that, we need to come to this equation. We studied that today. So we have kinetic energy is equal to EV, charge of the electron, times the potential, the applied potential across that tube that you can see. So if we try to work in this equation and try to modify it, so we can come to equation number 1, which is this one again. So we have E, velocity, magnetic field. We have MEVE squared over R. So what I did, I multiplied this by 2 and then divided that by 2. So that will give me this expression, which is the kinetic energy. So now, I can replace all of that, 1/2 MEVE squared, and have charge of the electron times the potential difference. So we'll have here 2EV over R. So this E right here, which is right here, can be cancelled with this E here, and we will end up with VE, which is the tangential velocity, is equal to 2 potential difference divided by R times magnetic field. And now I can substitute VE from here with 2 capital V over RB. The potential difference, the radius of the of this circular path, and here we have the magnetic field. So when we do that, we will have this very nice equation. Let's see. We know V, so V can be adjusted using that knob. So we can have V adjusted, that's totally fine. V can be calculated using this equation right here. So here we have a number of turns of Helmholtz coil, and we'll show you Helmholtz coil here. And maybe, guys, it's a good idea to do this for you. So maybe I can show you that. Just move that a little bit closer.
What makes them from just normal electromagnetic coils to Helmholtz coils?
What makes? So say that again.
So what about these coils makes them specially Helmholtz coils? Like
Yeah.
why is it worth having a name?
Yeah, so the thing that makes them special here, the number of turns here can increase the magnetic field. So you can control the magnetic field by increasing the number of turns. The current that flows here actually is the same, so there is no difference. You can control that by this node right here, but here we have 1.64 amp, so that's fine, it will be the same. But the thing that makes them special, by increasing the number of turns, that can make the magnetic field a little bit larger. If I double them, so what will happen? This is very important. If I double them, so I have one of them here and the other one here, that can help you to have kind of uniform magnetic field.
Okay.
And we will try to draw that on the whiteboard so you can see it. But again, you can use this to control the potential difference. You can use this to control the current. But the current should be fixed, so don't change that. Okay? So that's really nice. And I will try now to help you to see that. I will go a little bit back so we can see everything again. Okay. I will try to get everything down and then go to your question. So here is the tube, guys. Here is the electron gun. So you can see that you have the anode right here, you have the cathode right here. So that will accelerate the electrons. So the electrons will go like this, from this side to that side. During that trip, the electrons will strike with the helium gas atoms, and that will make or will create some de-excited electrons. Those de-excited electrons will create this kind of light. So, striking the electron by the helium atom will bring some energy to these electrons, but these electrons will lose this energy and get back to the same energy level, and they will lose some light that you can see right here. It is evacuated, so we don't have a mix of gases here. We should have like around 99.9% helium gas. And Helmholtz coils, these are the coils that I showed you right there. Let's come to the results. So, in today's experiment, guys, you need to change the potential difference. Keep current fixed, don't change that. The magnetic field can be calculated. So since we have fixed current, so the magnetic field is not going to change. Okay? Oh, actually the magnetic field should change because the magnetic field actually is function R. Yes. So when you change V, I is fixed, R should change, the radius of the circular trajectory, and that will change the magnetic field. But the whole combination here should give you, by the end of the day, E over N. So try to change the potential difference, like do that maybe 6, 7 times. So you can have like 6, 7 trials, and with each trial you can calculate E over M, and then average these values. So that will give you the average value for E over N. Another thing here, so let's see here, so this is the radius of this circular path. So this should be R. This should be R. This should be the radius of Helmholtz coil. Oh, sorry for that mistake. So capital R. This is the radius of Helmholtz coil. Okay. Yeah. So capital R is the radius of Helmholtz coil. So yeah, all of these are constant, so again, B never change, R will change based on changing V. But the question, how can we measure capital R? To measure capital R, the radius of Helmholtz coil, you can do this simple idea and try to measure that. There is an error. To figure out the uncertainty for this measurement, you can divide, you can look at the smallest value in this meter stick, which is 1 millimeter, divide that by 2. So that will give you the uncertainty due to this. Okay, and I think you are good. I'm just missing one thing here to explain. Yeah, let's explain that to you. So let's start with the uniform electric field. So to create uniform electric field, we need to have capacitor. So we have here positive side, we have here negative side. So we have uniform electric field. If you try to reduce the distance between those two plates, that will make this electric field like more uniform. But in general, what will happen, the electric field can go like this. That's possible. But here, the electric field is uniform. Now let's come to the magnetic field and see how can we get uniform magnetic field. So if we have a coil like this, and we have a current flow in this coil, so who knows the direction of the magnetic field? That direction?
From the right hand, control, right?
So this side toward us,
Oh.
and that side toward the whiteboard.
Yes.
Well, that way.
That way. So let's assume that we have here a wire and it has current. The current is going up.
Go around.
Around. Like this, you're right. And it is going like this, since the current is going up. So here, this is toward me, and this is toward the whiteboard, so that means I will have magnetic field in that direction. But the magnetic field lines are circles. To have uniform magnetic field, what do we need to do? We can have another circle that has current like this. So the current is going up, the magnetic field can go inside this direction. So we have magnetic field going like this. But outside, we will have closed path for these magnetic field lines. If I increase the number of turns here, and if I increase the number of turns here, so that will increase the strength of the magnetic field. And if I keep them closer and closer, so we'll have kind of uniform magnetic field. But if I have them like a little bit far away, so the magnetic field won't be, yeah, it will go like this. Yeah, it won't be uniform. So this can help to have as much as uniform magnetic field to help having this idea that you can see right here. Okay, so uniform magnetic field, this is the key. Okay, so do you have any questions?